see it that way. All right, so you can see on the agenda today, we're going to talk about the first page of worksheet 1 that we handed out last week. That was the assignment, is to finish up at least that first page. And then we're going to do a little demonstration as part of that out on the balcony with the bowling ball. Then we're going to talk a bit more about the stopper lab that is our project for tomorrow. And tomorrow is the big data collection day, so today we want to make sure you get any fine-tuned details you need to know. Make sure you get all your questions answered, get you divided up in your groups, and actually get you started pulling together some of your information in your lab journals and being really well prepared for tomorrow. And don't forget, we're going to look at worksheet 1, page 1 today, but the rest of it for you guys is due Friday. It's Thursday for A Day, Friday for B Day. So for you guys, we need to have the rest of worksheet 1 done by Friday. All right, let's go ahead and talk about worksheet 1 first. So on the first page, the question at the top is about a bowling ball or some kind of ball. I guess some reference says bowling ball specifically, but it's going in a straight line and it's curving, and you're trying to figure out how would you make it curve. Do you need one, Elijah?
Yes.
Okay. I've got extra copies over here. And so the question is asking, what do we do to make the object curve? So we're going to go out into the balcony here and try to simulate that a little bit. So if I can, I'm going to have to carry my computer. So if I can get, maybe Devin, if you can carry this out, Luke, if you can carry this out, and I'll grab my computer. And out on the floor, you're going to see some blue tape. Just go kind of make a circle around the blue tape so you can see the demonstration here. We'll have a couple students help us out with that. All right. Yeah, so go ahead and come on out. So Charlie, can you see the blue tape on my video?
Yep, yeah.
Not the one that's not the video that's in the classroom, but on my other one. So is it showing up okay for you?
Yeah, I can see like a pretty big like racetrack shape thing.
Yeah, so just like a straightaway with a curve. Good. All right. So who's got the ball here? Okay. Gonna put the ball down here. Luke, you want to go for us first? We'll get a few of you to volunteer here. All right, so the goal is to, using the mallet, push the ball along the blue path. It obviously starts straight, but then curves. So we've got linear motion and then uniform circular motion, or hopefully fairly uniform circular motion. You can tap it or you can push it, whatever you want. We just want you to try to follow that path. And for those of you that aren't participating right now, I want you to watch what has to happen to the force he applies, however he applies it, to make this work.
You don't need to just.
You can tap it or push it, but just only with the mallet. All right, good. So you see one technique there, just pushing it along with the mallet. Devin, you want to go next here? Let's take a few of you to demonstrate. And then you can use the same strategy or a different strategy. We got a lefty here, all right? All right, very good. So in the first two examples here, what do you notice about the change in force when it has to make the curve? Yeah, the force goes from being behind it, pushing it in a straight line, to being on the outside, pushing it back to the center. All right. Anybody else want to try? Got a couple demonstrations. See if you can beat the world record, land speed record here. Nobody? All right, anybody willing to show us tapping it? Because that also shows a little bit. All right. So instead of pushing it, just try to tap it and kind of accomplish the same goal. very good. And so you can see with one thing about the tapping that it shows is the first couple taps didn't do much, right?
Yeah.
It's like, yeah, you have to keep putting some force in there to break its inertia. It's at rest, so it wants to stay at rest, right? And so it takes a little bit of force to get it going, and it's a fairly massive object. It's not like a ping pong ball or anything, so it takes some force to get it to go, to get it to accelerate. Then once it starts moving, it's naturally going to go in a straight line. The only way to make it not do that is to provide another force that is directed back to the center, whether it's a constant force or whether it's a tap force. You see kind of the same result. Anybody else want to try before I go back in? All right, you go ahead and bring the ball back in and we'll go head back into the classroom. So could you see that okay, Charlie?
Yep.
Yeah. What do I thought? You just put it in that box over there for me. So the main point of that was to help you see kind of a visual of what first question on that worksheet 1 is asking. So let's switch gears to the first question on that worksheet. You see in the worksheet now, Charlie?
Yeah.
So there's no one right way to draw it. This is just an example. And hopefully you can kind of see from this example on the screen kind of what we witnessed out there on the platform, on the balcony, that the ball will naturally go forward in a straight line if it's already moving. If it's not, you're going to have to apply a force to make it do that. But then once we want it to start curving, we have to push it at an angle that's directed back towards the center of the circle. So this is just one representation. Some of you use more of like a cartoon comic strip approach to like frame by frame. Some of you had different approaches to it. But so it doesn't have to look like this, but something that shows you would actually have to change the direction of the force to always be pushing it back to the center if you want it to actually travel along that curved path. What do we call that center-seeking force? Centripetal. Good. So any questions about 1A?
Yeah, I think I have the wrong worksheet.
Oh, okay.
Wait. Is this the one, like, circular motion intro?
No, that was the one that was due last time.
Shoot. Okay. Oh, so this is like on topics or something. Okay.
Yeah, it should be on Axis Unit 3, Worksheet 1.
Okay.
Right underneath the intro.
Got it. Thank you.
All right, for part B, it says, while you are curving the ball's path, are the forces on the ball balanced? Well, if they were balanced, there would be no acceleration. But if something's moving in a circle, what kind of acceleration does it have to have? Centripetal. So if it has any kind of acceleration, whether it's linear or centripetal, there has to be an unbalanced force. Accelerations of any kind, and we're going to eventually know 3 different kinds of accelerations. Accelerations of any kind can only occur if there is a net force. And in this case, since it's a centripetal force that is the net force, it would be directed to the center of a circular path. So if we look at this free body diagram here, we can see that the ball, and the example we did out on the platform, we've got Fg, the weight of the bowling ball, pointed down because of the Earth's gravitational force field. We can see the normal force of the ground pushing up on the ball so that it stays on a flat, level surface of the ground. So those 2 vertical forces are equal and opposite and therefore balanced. But there has to be some other force directing it to the center of the circle. So remember, a free body diagram shows you what the forces look like at a single point in time. They're not showing you over time passing. So this is showing if I were looking at that bowling ball at a single point in time, the downward weight force, the upward normal force cancel. to curve along that path, there has to be an outward force pointing into the middle of the circle. So this free body diagram would be like, oh, kind of in this side of the circle, where if we're looking at the ball from the side, weight is down, normal is up, and there's an inward to the center of the circle net force. In this case, the net force is centripetal. Part C, is the ball accelerating? If so, what's changing about the velocity? So in the original description here, it says you're trying to curve the ball to make it turn in a smooth circle, as the picture indicates here, or draw a picture indicate it, and we can see it now. And so here it says, assuming the ball is not changing speed. So in other words, even if the ball is going at a constant speed, even if it's not speeding up or slowing down, it has to have acceleration to be traveling in a circle. Because to be traveling in a circle, there has to be an outside net force making it curve. And if there's an outside net force making it curve, forces cause acceleration. So it has to be accelerating whether it's speeding up or slowing down or not. Even if it is going at a constant speed, the direction would be constantly changing. Anything moving in a circular path, or even part of a circular path, will have a direction that's constantly changing along that circular path. I want to talk to you a little bit about some math connections here. And I know that, well, actually, maybe let me just create a slide and show it there. That way it'll show up on the recording. It'll be hard to see on the camera. So we'll come back to this in a second, but let's go here. Just enter a blank page, because I want to illustrate a couple things here. How do we calculate centripetal force? What's the equation for centripetal force? Chris?
Velocity squared over radius.
Velocity squared over radius would give me the centripetal acceleration. And then we'd have to multiply it by the mass. So that would be centripetal acceleration. If I multiply that by the mass, now I've got a force, mass times acceleration. Okay. Since it's an centripetal acceleration, so let me just jot that over here as a side note. Centripetal acceleration is v squared over r. So v squared over r is the acceleration. Acceleration times mass gives me a force. Since it's a centripetal acceleration, it's giving me a centripetal force. Now, in this example of the ball, and actually in most of the problems we solve, it's going to be true that the centripetal force, most of the time, will be the net force. Okay, most of the time, the centripetal force will be the net force for the scenario. Usually the other forces will all be balanced, and it'll just be the centripetal force that's causing the acceleration. Since we're looking at uniform circular motion, that's going to be the most common scenario. So what if the centripetal force was friction, like a car turning on the road and being able to maintain its curved path? There's friction between the tires and the road. What's the formula for friction force? Times what? I couldn't hear.
Normal force.
Normal force, good. All right, so the friction force is the normal force. So if I know that in the car turning the corner, if that friction force is the centripetal force, now I can take this equation, mu Fn, and set it equal to centripetal force, m v squared over r. And this is a strategy, a problem-solving strategy that's going to carry over for lots of examples in this semester. It's going to be one of the primary new strategies. First semester is mostly about learning new equations and how to apply them. Now it's going to be about, okay, learning a new equation, and how do I connect it to the stuff we did last semester? And so that's the key for this semester, is being able to do that. Now, how do we usually calculate the normal force? Yeah, question, Aiden, or?
Yeah, it was just about like how we can like connect the force of friction to like the centripetal force, because there's like a question asking about like max speed. So I mean, it makes sense like in a straight line, like if the acceleration is equal to the friction force, and that's like the max speed. But like, how would that really work with a circle? Because like the acceleration, I don't know. Does the question really make sense? What I'm asking?
I'm not sure I understand your question, but let me try to answer it, and then you can let me know if I'm on the right track. So we're switching gears from thinking about acceleration meaning speeding up or slowing down to now thinking about acceleration meaning changing the direction while it's not speeding up or slowing down, and specifically changing its direction so that it goes in a circle. So in the example I think you're referring to, and kind of what I'm talking about here, the acceleration we're referring to isn't speeding up or slowing down, it's this acceleration that's related to its tangential velocity, and it's not changing. The tangential velocity is constant, and divided by the radius, which is also constant, because we're only looking at uniform circular motion. So we're trying to figure out not what is the linear acceleration, because they're not equal. Linear acceleration and centripetal acceleration are not equal. They're two different things. The only thing that relates them is forces, because centripetal acceleration is caused by a force, specifically a centripetal force. Linear acceleration is caused by a force, some kind of linear force, but they're all forces. So forces is the connecting point. In this problem, if we're trying to figure out the maximum speed that the car could go, we're basically saying, when is the friction, the maximum friction that we could generate, equal to this maximum centripetal force that's required to keep it in a circle?
Oh, so maybe it's talking about like keeping it on the path.
Yeah.
Maybe.
So
Like,
like,
so that it doesn't like go away from the path or slide in.
right.
Okay, that.
Yeah, so if you're driving and you start turning, if you're going too fast, you won't be able to stick on the curb, right? You'll start skidding.
Yeah.
And so we're trying to figure out how much would that friction need to be so you don't skid, so that you actually do keep staying on that circular path.
So in that instance, would that be like inertia being greater than centripetal acceleration, or would that be? I mean, that wouldn't.
Yeah, the inertia is is the property of the matter that makes the object want to keep going straight. And so if there's not enough friction, if the friction force isn't equal to the centripetal force required, then the car either needs to slow down or change the radius of its curvature, or it's going to skid.
Oh, so the friction force was maybe greater than the centripetal force. So
it'd have to be equal to it. Or less. Yeah. Greater or equal to.
Yeah, because that would cause it to stay on.
Because it's static frictions. Remember, it's even though the car's moving, we don't want the tires to move across the road, right? So it seems like it should be kinetic friction because the car's moving, but we don't want the tires to slide on the road. So we really are looking at static friction, where the tires grip the road and don't slide.
Yeah.
And since static friction is that less than or equal to, because as long as there's enough friction, it doesn't have to be the maximum amount, right? It can be anything under that. When we calculate it, what we're always calculating is the maximum. And so anything less than that will be fine. And so if this is the maximum friction force based on the coefficient of friction and the weight of the car, we can determine how fast could the car be going and not break past that static friction. Because once it breaks past the static friction, part of the reason it's hard to recover is because kinetic friction, if you remember from last semester, kinetic friction is usually lower. So once you start sliding, it's harder to recover because you have to get it to the point where the static friction can take over again, but now you've got a lower coefficient of friction, so you just keep sliding until you can either slow yourself down by changing your velocity or changing the radius of your turn, and eventually you can get the static friction to take over again. Does that help?
Yeah, that makes sense.
Okay. So then back to my question. That's a great question. I'm glad we had some conversation about that. It brought out a lot of really important facts. But back to my question, how do we usually calculate the normal force for an object? As long as it's on a flat surface, what's true about the normal force? Chris?
It's equal to gravity or weight.
Equal to the weight, right? It's going to be the same as the weight. So how do we calculate the weight? Oops. What do we use to calculate the weight of an object? Mass times what kind of acceleration? Yeah, gravitational acceleration, or the Earth's force field of gravity. All right, and so then we would have this relationship, right? As long as it's a flat surface, the normal force and the weight force would be equal. We can find weight by mg. So what happens to the equation? Yeah, this cancels out. So does the mass of the car even matter? No. So if you are civil engineer, work for the highway department, you're putting on a new off-ramp, and you want to put the speed limit sign on this curve so people know how fast or slow they can go. This is the math you do to figure out what's the limit so that the cars won't skid off the off-ramp, right? We got a certain curvature. The off-ramp has a certain radius. So they know G, they're on Earth, right? They know the typical U. Now, this is just going to be for a standard tire against asphalt. So if your tires are better or worse, you're going to change that mu factor depending on what kind of tires you're using, right? But they'll use like a standard, what's normal rubber tire on asphalt? They use that coefficient. That's just 9.8. They know the curvature of the circle based on what the curve of that off-ramp looks like. And then they can find out what's the speed, and then they're going to put something lower than that, right? So if the maximum speed is 45, they'll probably make it 35. Yeah, Chris?
So theoretically, your tires were like sanded down, you would just slide off in a straight line, right?
Yeah, if you had a really poor coefficient of friction because your tires are really bad, the lower that number gets, the lower this number has to be, because G's not going to change. And if they've already set the curvature of the road, the R is not going to change. So if this gets lower, your speed has to get lower. Otherwise, the car's going to want to go straight. Or if you hit ice or hydroplane on a puddle of water where you lose friction. So this is under the control of the driver, right? This is under the control of the earth. This is under the control of the highway department, architects and civil designers that engineer the ramp. And then they can determine, okay, we need to encourage people to drive at this speed or lower. And they're never going to say, oh, they can go 45, so let's put a 45 sign up there. They're going to say, oh, they can go 45, so let's put a 30 or a 35, because they know most people are going to go more than what the sign says, right? Yeah. Yeah. All right, so that's what I'm wanting you to think through is centripetal force can be caused by all kinds of things, and this whole semester with this unit and future units, the key will be figuring out what's causing the centripetal force. So let's switch gears just real quick. I don't want to spend too much time on it, but I do want to show you one more example. What's the centripetal force that keeps the moon revolving around the Earth? Gravity. Okay, so that means the centripetal force, M, oh, there's too many bumps on my M there. mv squared over r, the centripetal force is gravity, which is g m1 m2 over r squared. Right? That's how we find the centripetal force between two objects. Well, if this is the moon and this is the earth, we're talking about the moon's centripetal force, right? The moon is what's traveling. What cancels? Mass of the moon doesn't matter. The mass of the earth isn't going to change, right? And then we can cancel out a factor on our r value as well. So if we multiply both sides by r, it cancels over here and reduces over there. So if we take g, the capital G, universal gravitation constant, times the mass of the earth divided by the radius of the earth, or the radius from the center of the earth to the center of the moon, we can figure out what the speed of the moon should be traveling around the earth. Okay. And so these are the kinds of problems you're going to be asked to solve when it comes to uniform circular motion. Identifying the centripetal force, friction, tension, gravity, whatever it happens to be, putting some equations together, often using some free body diagrams to help you do that, and then solving for whatever they might be asking, like how fast is the moon orbiting around the earth, or what radius is it if it's orbiting at this tangential velocity, so something like that. All right, so that's kind of a tangent, but I wanted to make sure that we start to see that because that's such a critical skill for this semester. I wanted to at least introduce that idea. Any questions about that? All right. Let's go back to the worksheet and wrap this up. On number 2, it says the airplane banks and makes a wide circle. Draw a force diagram for a head-on view of the banking plane. Name the force that allows the plane to travel in a circle. So if the plane is flying level, not changing altitude and not banking at all, not leaning either way, there's going to be some angle to the wings so that the air can hit the wings and provide lift. And when that lift by the air hitting the wings balances the weight of the plane, the plane stays at a certain altitude. So the plane can slow down or change the flaps on the wings to try to adjust its altitude, right? But if it wants to turn, it's going to have to somehow change the angle of the wind hitting those wings. And so that's why banking works. When a plane banks, now the wind is hitting the bottom of the wings at a different angle. There's two components to every angled force. In this case, the angled force is the wind pushing up against those wings. And that means there's a vertical force and a horizontal force. What is the vertical force providing, this vertical component? Lift, so the plane doesn't change altitude. What's the horizontal force component providing? The centripetal force that makes it turn. So we could use a free body diagram. We could figure out using our trig, what's the equation to find this horizontal component, and set that equal to mv squared over r. If we were doing a math-based version of this, right? We could actually figure out what angle do we need to turn at if we wanted to follow a certain radius of curvature. All right, so the horizontal component of that air pushing under the wings is what causes the plane to turn. The vertical component just keeps it lifted in the air so it doesn't change its altitude. Any questions about number 2 here with the plane example? Let me just take it one step further with the math here. If they give you the mass of the plane, how do you find FG? They give you the mass of the plane, how do you find FG? If they give you the mass of the plane, how do you find FG? Yeah, times 9.8 or 10, right? Just mass times acceleration due to gravity. That is equal to this. All they would have to give you is the mass of the plane to get you started. Because if you know this, you know this. And then they maybe give you the angle there. Then if you know the angle on one side, you can find any of the other sides, right?
How do we know they're equal? Because it's not falling?
It would have to say something like the plane is maintaining altitude or something, yeah. I mean, it could be that the plane was declining or ascending. But generally speaking, they would, I imagine, say the plane is keeping its constant altitude at banking at an angle of 30 degrees or whatever. And then you know the angle, you know the weight has to equal that y component because it's not rising or falling in altitude. And then you can find that x component, just thinking through the trig of it. All right, so we'll stop there for worksheet 2. I just want to make sure you had a chance to finish up the front sheet. And any questions on that before we put that to rest for today? All right, so now that we've talked through some of that math, if you haven't worked on page 2 and 3, then that may help you kind of process some of the math you have to do on the car problem on the next page. I know some of you already got that far, but if you haven't, hopefully our conversation today will help you figure that out. So finish up the rest of worksheet 1 for Friday. Wednesday, we're going to be collecting data for the lab. So that's what we need to do next, is make sure we're ready for that. All right, so let me talk to you a little bit about the lab, then I'll have you get with your groups and make sure you're set. You're done at 12:50. All right, so we're good. So this experiment is a little bit like 3 mini labs. The first one is we're going to keep the radius constant and the stopper mass constant, and we're just going to change the tension force. All right, so just to make sure it's real clear, practically speaking, what's going on, you're going to choose a radius, you're going to measure it out, and you're going to have someone spin the stopper so that that radius is what you chose. And one thing you can do to kind of measure that is you can use tape, or you can use these little alligator clips, and you can clip it on here so you can see that it's not rising or falling. Because it's kind of hard sometimes to see if this is rising or falling because it's spinning and shaking and stuff. But if you have this clipped to the string, you'll be able to see if it's going up or down. Okay, or put a piece of tape on it or something so you can see it. So the radius will stay constant, so the person needs to spin it at a constant rate. The stopper mass isn't changing because we just have one stopper on there and it's fixed. But then you're gonna do one set of data with maybe 500, and then one with 400, and one with 300, and one with 600, and you're gonna just keep changing the weight of this hanging down here, and keeping the radius whatever you chose it to be. So the person doing the swinging is gonna have to adjust the speed based on what this is, so that the radius is the same for every trial. Okay, is you tracking with me okay on that? Making sense? Or any questions about that first setup? All right, so radius is determined. You'll decide what it should be. Stopper mass is fixed. You're only going to use one stopper. You're going to adjust the tension, and then the person swinging is going to have to adjust the speed they swing it at so that it stays constant with radius with the new weight. All right, then you're going to take that data and do some graphing so that you can develop a mathematical and graphical relationship between the tension force, this is causing the tension force, and the tangential velocity, which you'll have to calculate from the things you measure. All right, you've got some equations for that, so you'll have to process that. There's some hints on the back of the rubric I'll give you here in a couple minutes. You'll also find the mathematical and graphical representation or relationship between the tension force, this, and the centripetal acceleration, which you'll also have to calculate. So the tension force is just going to be this in newtons, right? So you have to take this mass times g. Tangential velocity and centripetal acceleration, you're going to have to calculate using the equations we've learned. So centripetal acceleration, v squared over r. You'll measure the r and you'll determine v. You can determine v by thinking about what's the circumference, what's the period, right? Circumference divided by period gives you tangential velocity. Okay, so that's how you'll do the first mini lab. The second one, you're going to keep the tension force constant, so the weight that you have hanging should be the same the whole time. And you're doing this one first, so you should know a weight that works well with the stopper you're using. Okay, and then the stopper also still not changing, still using the same stopper. Now you're going to change the radius. So run one trial where it's 20 centimeters, one trial where it's 40 centimeters, one trial where it's 60 centimeters. Now I will comment that for the first mini lab, number 1 here on the screen, you might be able to get, you should probably be able to get 8 different masses, like on our 8x10 rule, because you can do all kinds of different masses. We got all kinds of things back there. You can nest them and come up with all kinds of arrangements. You may or may not be able to do the times 10 though, because I don't want you to go above a kilogram, because I don't want the string to break and have the weight fall on somebody's toes, all right? And so since we're limiting our range of mass a little bit to create the tension force, you should be able to get 8 different trials, but maybe not a span of 100 or a multiple of 10. For this one, you're only using a 1.5 meter string or so, so getting 8 different radius differences, if you're only changing it by a few centimeters, it's going to be really hard to do that consistently. It probably needs to be about a 10 centimeter at least change between each one. So you might not get a full 8, but try to get at least 5 or 6 different radius measurements, okay? And you will for sure not, well, not for sure, but most likely not be able to do a whole times 10 for this one. So I want you to strive for as much of the 8x10 as you can, but knowing you won't probably be able to actually achieve it, okay? For that one, radius versus tangential velocity. Now on the rubric I'll give you here in a minute, it also says radius versus centripetal acceleration, but I've taken that out of here just because we only have one day to collect data, and I want to try to trim it down a little bit. It's on the rubric, so I left it there in case you want to try to evaluate that and you have time, but this is what needs to be done, right? And then the third one is in red, and it's also got asterisks beside it because this is like, if you have time, do this, but make sure you get 1 and 2 done first, all right? And on the third one, keep the tension force the same, so whatever weight's hanging, don't change that. Keep the radius fixed, so if you choose 50 centimeters, keep it at 50. And then you're going to keep putting on different stoppers, because we've got several different sizes. In this box is where all the tubes are, the string, these little clips if you want to use these, or you can just use tape. And then I think all the stoppers in this box are this number 10 size, the big size. But we have a bunch of other sizes in here. So there's 8s and 4s and 7s, and so you can try all different kinds in here. That takes a little longer because you got to untie one stopper, tie another stopper on, and if you have time for that, again, you will not by any means be able to try 8 different stopper sizes, but maybe 2 or 3 at least if you have a chance, okay? And we'll have different groups using different stoppers. Make sure you do record the mass of the stopper somewhere so we can know how it varies from group to group. We might be able to share data from one group to another so you can see if the mass of the stopper is making any change. If you do get this data, here's the graphs that I want you to strive for, but you have to get all the data collected tomorrow. So we may have to do this sort of corporately, and we'll kind of figure that out. So on the rubric, there's some little marks by it to show you that we may or may not be able to do that. So in the end, you should have 3 data tables if you can do all 3 of these steps, 2 for sure, hopefully the third one. All right, so that's why we got these asterisks here. You should have 5 graphs potentially, 2, 1, 2. If at least 3, right, and hopefully these 2 as well. And some of them will need to be linearized. And so if it needs to be linearized, do so. If not, then don't. So I put a question mark there because it depends on how many you get, and I don't want to reveal which ones are linear and which ones are not. And then in your analysis, we want you to examine the graph features. So what are the 3 parts of any graph we always try to evaluate? Area under the curve, slope, y-intercept. So I want you to try for every graph that's linear. You only have to do, I can maybe type that in just as a reminder here too. You only have to evaluate those graph features for the linear graphs. All right? And then you're going to draw some conclusions. So what is the relationship between radius and tangential velocity, for example? So you'll put that in your conclusion as well for each of those Toa-Gamma statements we're testing. And then comparing. What is the centripetal force, which you'll be calculating, compared to the tension force, which you'll know? All right, so how do those 2 things compare as you're going through and evaluating your data? So that'll be part of your conclusion. And all of that is here on this rubric. So I'll put these over here. And let me divide you up into your groups. You can grab a rubric and you can have a little brainstorming here for the last couple minutes to make sure you know who's in your group. And maybe brainstorm, are we going to try to use video? Who's bringing the phone? Are we going to try to just use a stopwatch? What are we going to do? So we'll give you a few minutes to do that. Here are the groups. Let's make sure, yeah, Charlie and Dominic are in 2 different groups. That's good. So do you know when, do you think there's a chance you'll be back tomorrow, Charlie, or not yet?
I'm feeling fine, but I do have COVID, so probably not.
Probably not.
I don't anticipate I'll be back until, honestly, like next week.
Okay, all right. I have a feeling that may be the same with Dominic. So we'll, if that's the case, we'll try to work something out for you and Dominic. And I'm not sure, since Kenny's not here today. Actually, since you're pretty sure you're not going to be here this week, let's just adjust that a bit. So let me take, and I imagine he's not going to be here tomorrow at least. So let's just redo this. All right, so here's your groups. Group 1 will be Devin, Luke, and Kenny. Group 2, Parker, Grace, and Aiden. Group 3, Chris, Curtis, and Elijah. Group 4, Lexi, Matthew, and Sheldon. And Group 5, Jordan, Jenna, and Dante. So go ahead and get with your groups. Make sure you get a rubric. Kind of brainstorm for a few minutes to make sure you know what your plan is for tomorrow. And then we'll dismiss here in a few minutes. And Charlie, if you're unable to get back at all this week, what we may have you do, there's a similar one to this you can do online as a simulation through Gizmos. So we can talk with you and Dominic about whether you want to just do the simulation or whether you want to try to get together and do the actual hands-on when you get back.
Okay, great. Yeah, sounds good. Yeah, and then I haven't done any of those worksheets at all because I got sick right before like Thursday or whatever. So I'll do that too, and
Time to get caught up on
makes
that.
sense. So
All right, sounds good, Charlie.
thank you very much. Bye.
Yep.
The least amount of force that we need to get up.
Yeah.
We could